for Lecture 15, Section 2. This video will cover thermocouples. Thermocouples are part of thermoelectric thermometry. They are very commonly used to measure temperature in a wide variety of applications. You have used them in lab already. This table summarizes some of the advantages and disadvantages of thermocouples. They are rugged and the dissimilar metal junctions are easy to make in the field. They can be used to measure temperature over a wide range of many common needs. The off-the-shelf precision is only plus minus 1 degree Celsius, but they can be calibrated to greater precision. Thermocouples do have some disadvantages that need to be managed. In many cases, the disadvantages can be managed fairly easily, hence thermocouples are common devices. Thermocouple dissimilar metal junctions generate a small voltage or electromotive force based on temperature. Unfortunately, the relation between the electromotive force and temperature is nonlinear. We generally prefer sensors that have linear relations between the input and the output, but thermocouples have nonlinear relations. So the relation has to be found and used. Finally, thermocouples require a second reference temperature input. We will talk about reference temperatures more later. So while thermocouples are common, the disadvantages need to be overcome. Let's begin with a bit of information about the physical principles behind thermocouples. The first principle is called the Seebeck effect that was discovered by Thomas Seebeck in 1821. He discovered that a current would flow in a circuit made of two dissimilar metals when the two dissimilar metals junctions were at different temperatures. So to have a Seebeck effect, you need two metal wires that are connected at the end of the to make two dissimilar metal junctions, and the two junctions need to be at different temperatures, T1 and T2. Then you will get a current in the circuit. The Seebeck effect has some consequences if we want to use the principle to measure an unknown temperature. We need to know one of the temperatures, which is called the reference temperature. In the old days, an ice bath at 0 degrees Celsius was used as the reference temperature because it was fairly easy to create. We also need to know the relation between the two dissimilar metals and the electromotive force generated. Electromotive force can be abbreviated as EMF. Finally, we need a way to measure the current. Will adding a measurement device in the circuit mess up the system? Do you think so? A measuring device will add new dissimilar metal junctions and they will generate EMF too. The laws of thermoelectric circuits are used to summarize the relations needed to make thermocouples work as temperature sensors. There are 3 laws and some consequences. The law of homogeneous metals states that a current cannot be generated without having dissimilar metals. If you make a circuit with one homogeneous metal, you won't get any current flow. One consequence of the law of homogeneous metals is that the temperature along the homogeneous metal wires does not affect the EMF generated. That means that We do not need to worry about the temperatures between the two junctions because the two wires were homogeneous, and homogeneous metals do not generate any EMF as temperature changes. Conversely though, if the wires used to make thermocouples are not homogeneous, if they are non-uniform in some way, then they might generate an electromotive force. So the manufacture and handling of thermocouples needs to meet high standards to produce uniform metal wires. The second law, the law of intermediate metals, is given here. It basically says that if we have intermediate metals and multiple dissimilar metal junctions, the EMFs they generate sum to zero if all of the intermediate junctions are at the same temperature. So we can add equipment to the circuit, and as long as all of the equipment junctions are at the same temperature, the total EMF is zero, and it does not affect the measured EMF. A second consequence is that we can use solder to make thermocouple junctions, and the third metal does not affect the EMF generated. This is great news because this makes it easy to make junctions in the field using normal soldering techniques. Okay, so now we know that we can add a meter. The question is, which way do we want to add the meter? And let's assume that meters use a third metal. So adding the meter adds two new dissimilar metal junctions. The little red boxes represent isothermal bars which are at the same temperature. With isothermal bars, we apply the law of intermediate metals by making sure that the new intermediate dissimilar metal junctions are at the same temperature. Hopefully you will see that the top option is the preferred method for inserting a meter into the circuit. The reason is that for both circuits, we will need a reference temperature, and the common practice is to use the temperature of the isothermal bar as the reference temperature. With the top option, we do not need an external reference temperature that we would need for the bottom option. Hopefully you recognize that the top option was how to attach the thermocouples to the PDAC 55 units in lab. The third and final law of thermoelectric circuits is the law of successive or intermediate temperatures. The important consequences of the law of successive temperatures are that we need to know the reference temperature. We cannot have two unknown temperatures. The second key consequence is that we need to know the metals being used and the relation between EMF and temperature for each metal. They are different for different metals, so we need to know the metals being used. In lab, we told you that you were using copper constantan thermocouples. As I mentioned before, if you have a simple two-wire circuit and you need an external reference temperature, the standard reference temperature is an ice bath. In the old days, before our modern electronics, there were standard reference tables that listed the EMF for each temperature, typically down to 1/100th of a degree Celsius. With modern electronics, we measure the temperature of the isothermal bar inside the meter with an RTD, thermistor, or an integrated circuit thermal transducer. Then we need to tell the meter which metals we are using, so that the meter uses the correct equation to calculate temperature based on the EMF measured. This slide illustrates how we connect thermocouples to our meter or to a PDAC 55. We have an isothermal block which serves also as a reference temperature which we need to measure with another device. So if we need another temperature sensor in the meter, why use a thermocouple? Why not use the other temperature sensor? Well, the answer lies among the advantages of thermocouples you saw at the beginning of this video. Thermocouples are rugged, inexpensive, work over wide temperature ranges, and provide adequate precision. The other sensors, RTDs, thermistors, and integrated circuits have disadvantages that make thermocouples a popular choice. There are 7 different combinations of thermocouple wire. The course packet lists the 7 combinations and their corresponding letter. You can read the characteristics in the course packet. The selection characteristics include the amount of EMS generated. More EMF is better. Nowadays, with our electronic devices and the capabilities of the microchips in them can easily handle polynomial, the nonlinearity is not a big issue. Finally, some thermocouple wires work better over different temperature ranges. For example, Type J thermocouples are used for temperatures from -40 degrees Celsius to plus 750 degrees Celsius, while Type S is used for very high temperatures, up to 1600 degrees Celsius. Junction corrosion and oxidation are important selection criteria too when measuring temperatures in corrosive environments or at high temperatures. One of the disadvantages of thermoelectric circuits is that the relation between EMF and temperature is nonlinear. The polynomial equation used for type T thermocouples is a 7th-order polynomial. The coefficients are listed in the course packet. Note also that there are different polynomial coefficients for different temperature ranges. The course packet gives the polynomial coefficients for temperatures from -200 degrees Celsius to 0 degrees Celsius, and for temperatures from 0 degrees Celsius to 400 degrees Celsius. So if you want the polynomial for other thermocouple wire combinations, you can go to the National Institute of Standards and Technology, aka NIST website. This brings to the end of Lecture 15, Section 2 video. The next video will cover practical thermocouple measurement issues. Please write down any questions you have and bring them in class and lab.